What's up, guys? Today I'm going to go over the power rule, or more specifically proving the power rule without using the power rule, hence it being a proof. So anyway, for those of you who are familiar with the power rule, that says is the derivative of x to the n is equal to n times x to the n minus 1. That's the power rule. My question on my exam yesterday was asking for the derivative of x to the n without using the power rule. This is the initial function for the power rule by definition. This is the start of the definition of the power rule. But anyway, let's solve this without the power rule. So let's approach it with implicit differentiation. Let's write it as its original function, y equals x to the n. Now you could also write f of x, but for those of you who are already in calc, you know f of x and y are the same thing. So anyway, first, we need to take that n and bring it down in front of the x, because how can you attack something, especially when defining the power rule, how can you approach this specific problem with a variable as an exponent? So how can we get this exponent down? Well, let's take the natural log of both sides. ln of y equals n ln x. Now you see I've written this n in front of this ln of x. When you do the natural log of something raised to an exponent, you bring that power down. This is not the power rule, even though we brought the power down. This is not the power rule. This is just how natural logs work. We haven't taken any derivatives yet. Now, once we take our first derivative, let's start with the ln of y. When you take the derivative of something that is the ln of something, you're going to write 1 over that variable, or number, whatever. So we have 1 over y. And because it's implicit differentiation, we also get a dy dx out of it. That's the same as writing y prime. And also, it's best to think about this not as a fraction. This is not a fraction. It's literally its own variable. You can multiply this over if you want, just combine them. That would be the same as writing y prime over y. But Newtonian notation is kind of garbage, so we're going to stick with Leibniz notation, especially for implicit differentiation. It just looks nicer too. So anyway, now that we've taken the derivative of the left side, let's take the derivative of the right side. So n is a constant. N is a number. The derivative of a constant is 0. Now, why that's important for this specific problem, because we're going to use something called the product rule. Now, what that says is f prime times g plus f times g prime is our derivative when we have two functions being multiplied together. Here we have the function that is n, and we have the function that is ln of x. So we know that that's going to be 0 for our f prime, so that's just going to make the f prime times g 0, so we don't have to worry about it. Now let's go to f times g prime. Well, our f is n, and our g prime, remember, derivative of ln of anything is 1 over that thing. So we get n times 1 over x, or just n over x. Now, remember I was just saying that this can be y prime over y if you want to think about it, how it actually is. I just read the dy dx because I do prefer Leibniz notation. So let's get this dy dx by itself. The same as algebra, you're going to have to get a specific variable on its own. So let's multiply this y over. So we get dy over dx equals y times n over x. But because we're in calc, we have to have this in terms of one variable. So remember at the beginning of the problem, we had that original function. We have what y is equal to. This is just like substitution in algebra. So now that we have something that, we started with what y was equal to, so let's just replace that. So now we write x to the n power times n over x. Now let's multiply these over. X times n, I'm going to write the n over here so you can see where this is going, to the n power. All of that's going to be over x. So let's reduce this. Let's get rid of that x. And how we could reduce that is by reducing this power. Remember with exponents, if you're dividing the same variable, you subtract from the exponent. However many exponents are down here, in this case it's 1, you subtract 1 from that exponent. So if we want to get rid of this denominator, we'll write n times x. We got rid of that denominator, so take away 1, because this was x to the first power. Take away 1 from that n, so we get n minus 1. And look at that. That is just like the power rule. It is literally the power rule, and we've just proven that with implicit differentiation. And if you want to go a little bit further, I don't know, let's say this.